I want to start today with a reality check, a number that honestly well, it shocked me when I first read it in the research for this deep dive.
Okay.
We look at the news, and it feels like artificial intelligence is just taking over the world, right?
It's everywhere.
Every headline, every product release, it's all AI all the time. But the reality on the ground is different. Research indicates that a significant percentage of enterprise AI projects, we're talking estimates as high as 85%, never make it into production.
It's a staggering statistic. It really
They
is.
just die on the vine. They essentially evaporate before they ever see the light of day.
Think about the scale of that waste. I
Yeah.
mean, you see all this hype, all this venture capital pouring into AI, companies scrambling to hire data scientists at these massive salaries, buying up GPU clusters.
Millions, sometimes billions of dollars.
Actually, and yet, nearly 9 out of 10 times, these initiatives end up as expensive experiments that never actually solve a real-world problem. They end up as, a slide in a PowerPoint deck that gets archived and forgotten.
Exactly. And the burning question is, why? You'd assume it's because the technology isn't ready yet, or maybe the math is just too hard.
Right, that the models aren't smart enough yet.
But according to the material we're diving into today, that's almost never the case. It's usually not because the math is wrong. It's not because the computer isn't powerful enough. It's because the engineering and, even more importantly, the problem definition are missing.
Right. We're sort of moving past the magic phase of AI. For the last few years, it's been a bit of a magic show. Look what it can do. It wrote a poem. It drew a picture of an astronaut riding a horse.
Which is cool, but it's not a business plan.
It's not a business plan. And today is about the nuts and bolts. We're looking at a source called the AI Engineering Bible by Thomas R. Caldwell. And despite the rather grand name, I wouldn't call it a dry academic textbook. It reads much more like a field manual.
A survival guide.
Precisely, a survival guide for building systems that actually work. It strips away the buzzwords, which, let's be honest, this field is absolutely drowning in, and it looks at the actual life cycle of an AI system.
Design, build, deploy, scale. The whole thing.
The whole journey from idea to impact.
So here's the mission for this deep dive. We're going to strip away the hype. Whether you're a manager trying to figure out why your budget is blowing up and you have nothing to show for it, or a coder trying to transition into the AI space, or just someone who's insanely curious about how this stuff actually gets built behind the scenes, this is for you.
We're pulling back the curtain.
We are. We're going to explore the architecture of AI to prevent you from building expensive toys.
We want to help you build tools, not toys. That distinction is everything. A toy is a proof of concept. A tool is something that reliably solves a problem at scale.
I love that distinction. So let's start at the very beginning. Section 1 of our dive. The source talks about something called the trap of solutionism, which, it sounds like a philosophy term, but it's actually a huge engineering pitfall.
Solutionism is the foundational error. I mean, the source is really clear on this. It's the primary driver for that 85% failure rate we just talked about.
So what is it exactly?
It's the idea that people start with the solution rather than the problem. You get a directive from leadership or from the market that says, we need to use AI. It's not, we need to solve this problem. It's, we need to use this technology.
Right. It's the classic hammer looking for a nail scenario.
Yeah.
You have this shiny new hammer called AI, so suddenly everything in the company looks like a nail.
Exactly. You get a vague goal like, we need to use AI to improve customer experience.
Now, playing devil's advocate here, that sounds like a perfectly reasonable goal. Improve customer experience. Who doesn't want that? Any business would want that.
Everyone wants that, of course. But as an engineering constraint, it's useless. It's a trap because it lacks any specificity. If you hand that goal to an engineering team, they don't know what to build.
They have no target to aim for.
None.
Mm.
Should they be building a chatbot, a recommendation engine, a sentiment analysis tool for email support, a faster website? It leaves the door wide open for building cool technology that doesn't actually move the needle on any business metric.
It's too vague. You can't write code for better experience. You can't measure it.
Exactly. And Caldwell argues that the fix is extreme, almost painful specificity. You have to move from a qualitative wish to a quantitative target. So instead of improve customer experience, the goal needs to be something like reduce fraudulent credit card transactions by 85% while keeping false positives below 2%.
Okay, now that is a world of difference. That gives you a clear target. You have a metric for success. But I want to pause on that second part, the false positives below 2%. Why is that constraint so critically important?
That constraint is, in many cases, actually more important than the goal itself. This is where the source really highlights the disconnect between model accuracy and business value. It's where the engineers and the business side often stop speaking the same language.
Because you can have an incredibly accurate model that actually destroys your business.
100%. Let's stick with the fraud example. If my only goal is to stop 100% of fraud, I can write a very simple program right now. It doesn't even need AI. It just has one line: block every single transaction.
Technically, you've achieved zero fraud. The model is perfect by that metric.
Technically, I have a perfect model. I hit my goal, I get a bonus. But commercially, it's an absolute disaster. I have zero revenue and millions of angry customers who can't buy anything.
So the false positive rate is the guardrail.
It's the guardrail that keeps engineering aligned with the business reality. You need to define the failure state. The alignment isn't just, is the math right? It's, does this actually help the business context it lives in without causing unacceptable harm?
So it's about boundaries. It's about saying, we want to solve X, but not at the cost of Y.
Precisely. And this leads us to a really heavy cautionary tale from the source regarding hiring algorithms. This is a classic example. I think many listeners might have read headlines about this over the last few years, where major tech companies tried to automate reviewing resumes.
Oh, I remember reading about this. The idea on the surface was great, right?
Yeah.
Let's remove subjective human bias from hiring. Just let the data decide.
That was the hope. And it's the textbook case of framing the problem wrong. The goal seemed logical on its face. Find candidates like our current top performers.
And since the company had successfully hired people in the past, and those people were doing good work, the historical data should be gold.
Right. That was the assumption. But the problem was the framing. By saying, find candidates like our current ones, the AI didn't learn to look for skills. It didn't look for Python programming or project management or critical thinking. It looked for patterns in who got hired historically.
It was just pattern matching on resumes. It was looking for correlations, not causation.
Deep, subtle correlations. And if the company had, over decades, historically hired mostly men or people from specific Ivy League universities or people who played lacrosse,
The AI learned to penalize anyone who didn't fit that demographic profile.
it replicated and then amplified the historical bias. The source mentions a specific example where, if the dataset showed that Women's Chess Club appeared on resumes that were rejected in the past, the AI learned to automatically downgrade any resume that mentioned Women's Chess Club in the future.
It's horrifying.
It wasn't judging capability, it was judging similarity to the past. It wasn't finding the best talent, it was cloning the past.
And here's the really crucial part of that story, I think. The engineers didn't do anything wrong from a coding perspective. The code wasn't broken.
Not at all. They didn't write a be-sexist line of code. The math worked perfectly. It optimized exactly what it was told to optimize. The failure was entirely in the problem definition. They asked the wrong question.
That is a massive distinction. It really drives home the point that AI is like a genie in a bottle. It gives you exactly what you ask for, not what you meant to ask for.
It's a great analogy. It's literal to a fault, and it has no common sense or ethical framework unless you explicitly build it in.
So the key takeaway from this first section is really that success begins before you write a single line of Python. It starts with asking, what exactly are we trying to solve, and who might this hurt if we get it wrong?
What are we solving, and how do we measure failure? If you can't answer those two questions with extreme clarity, do not start coding. Go back to the drawing board.
Okay, so let's say we've done our homework, we've avoided the solutionism trap, we have defined the problem correctly, we know what we're building. Now we need the raw material, we need the data. This brings us to section 2 of the deep dive, the fuel.
And the source makes a very strong point here to move the conversation away from just gathering data, which sounds like a one-time event. It talks about a data life cycle.
I like the analogy used here. It says, most people treat data like mining for oil. You dig it up, you process it, you burn it, and you're done.
Mm-hmm.
But Caldwell says data is more like a garden.
It's a living asset. I love that framing. If you stop tending to it, it dies. Or, in technical terms, it degrades. This introduces the critical concept of data drift.
Explain data drift to me. Because, my intuition says if I have a spreadsheet of sales from 2019, those numbers don't change. The file doesn't rot on the hard drive. So how does it drift?
The numbers themselves don't change, but the world around them does. The relationship between those numbers and reality changes. It's about context. Imagine you trained a model on shopping behavior using data from 2019. It learns that people buy suits on weekdays and movie tickets on Fridays.
Okay, that seems like pretty standard, predictable behavior.
It was. Then 2020 hits, the pandemic. Suddenly, everyone stops buying suits and starts buying sweatpants. People stop going to movie theaters and start subscribing to streaming services. Your model, trained on 2019 data, looks at a customer in 2020 and makes completely wrong predictions because the underlying patterns of human behavior have radically shifted.
The data has drifted from reality.
Exactly. The statistical properties have changed. If your data strategy is static, if you just train it once and leave it, your model becomes obsolete the moment the world changes. You have to constantly monitor for this drift and retrain the model with fresh data. That's the tending the garden part.
That makes total sense. So you have to constantly feed it new data. Now, where do you get this data? The source outlines three main strategies: internal, external, and the really interesting one, synthetic. Internal seems obvious. That's your own company logs, your sales data.
It is, and it's usually the most valuable because it is unique to your business. It's your secret sauce. It describes your customers' behavior with your products. But, and this is a big but, it's often messy, unstructured, full of holes, and riddled with internal biases we just discussed.
Then you have external data.
Right, filling in the gaps. If you're a logistics company, your internal data is your truck routes and delivery times. External data is the weather report you pull in from an API to predict delays from snowstorms, or the real-time traffic data you get from Google Maps.
It adds context that you don't have internally. But the one that really caught my eye was synthetic data. This feels like it's straight out of science fiction. We are artificially generating fake data to train our AI.
It's becoming standard practice, and it solves two huge problems that are often showstoppers for AI projects: privacy and scarcity.
Okay, let's tackle privacy first. How does fake data help with that?
Think about training a facial recognition model. To get a good Face ID system for a phone, you need millions, maybe tens of millions of diverse faces. You can't just scrape millions of people's faces from social media without violating every privacy law on the books and getting sued into oblivion.
Right, that's a legal and ethical nightmare waiting to happen.
Absolutely.
Yeah.
So what do? You use computer graphics, basically high-end video game engines like Unreal Engine, to generate photorealistic faces of people who do not exist. You can control the age, ethnicity, lighting conditions, angle.
So you train the AI on fake people.
Exactly. You teach it the fundamental geometry of a face, the way light hits a nose, the way a shadow falls on a chin, all using data that doesn't belong to any real person. Then, when you deploy the model, it works on real people because it learned the general patterns. No one's privacy is violated in the training process.
That's incredibly smart. So what about the second problem, scarcity?
This goes right back to our fraud example. Real fraud is actually rare in a well-run system. Maybe 0.1% of your transactions are truly fraudulent. This is what's called an imbalanced data set.
So you don't have enough bad examples for the model to learn from.
Precisely. It's like trying to learn a language by hearing one new word a day. You'll never get fluent. The model might just learn a lazy rule. Always predict not fraud, and it will be 99.9% accurate, but completely useless.
So you use synthetic data to create more examples of fraud.
Right. You study the patterns of real fraud, and then you generate thousands or even millions of fake fraudulent scenarios, weird spending patterns, impossible location jumps, massive purchases at 3 a.m. from a new device. You flood the model with these edge cases so it can learn what to look for.
It's like a flight simulator for the algorithm. You let it crash the plane 1,000 times in the simulator so it learns how not to do it in real life.
That is the perfect analogy. You expose the AI to the most extreme situations in a safe, controlled environment so it knows how to handle them in the wild.
But before we can get to the training, there's this whole section on what the source calls the unsexy work: cleaning and pre-processing.
Ah, yes, the janitorial work of AI, data wrangling.
I feel like this is the part everyone skips in the movies. You see the cool montage of code scrolling on a screen, but you never see the data scientist spending 3 weeks deleting duplicate rows in a massive spreadsheet.
Exactly, but this is where the war is won or lost. Most data scientists will tell you they spend 80% of their time on this and only 20% on the actual modeling.
So why is this so critical? I mean, can't modern AI just figure it out? It's so powerful. Why can't we just dump the raw, messy data in?
Because models are mathematically literal. They are incredibly powerful pattern matchers, but they don't have common sense. The source lists a few specific techniques that are absolutely non-negotiable. Deduplication, for one. If you have the same customer listed 3 times in your data because of a database glitch, the model overweights their behavior and thinks it's 3 times more common than it really is.
Skews the whole model.
Completely. And then there's normalization. I loved the example given here, the kilometers versus millimeters problem. This is a classic rookie mistake that can completely invalidate your results.
Walk us through that. Let's really break it down.
Okay, suppose you have a data set for predicting house prices. You have a bunch of features. One column is distance to the nearest school measured in millimeters. Why millimeters? Who knows, maybe the sensor data from some mapping API came in that way, so the numbers are huge, 5 million, 10 million. Another column is number of bedrooms, which is a small number like 2, 3, or 4.
So in the data, the model sees a column with the number 5,000 and another column with the number 3.
Precisely. And the model, just looking at the raw numbers, assumes the distance feature is 1,000,000 times more important than the number of bedrooms, just because the number is bigger. It doesn't understand units. It doesn't know what a millimeter is versus a bedroom. It just sees the magnitude of the number.
So it would basically ignore the number of bedrooms entirely.
It would treat it as statistical noise, so you have to normalize or scale them. A common technique is min-max scaling, so that both columns are squashed into a range between, say, 0 and 1. Now they are on an equal footing. They're comparing apples to apples. If you skip this simple step, your model is garbage.
That is wild. It's such a simple, fundamental thing, but it breaks everything if you miss it. And then there's the issue of missing data. What do you do when there are just blank cells in your spreadsheet? Do you delete the row or do you guess?
Imputation is the technical term for guessing, and it's a really risky business. If a customer didn't fill out their age, for example, do you guess their age based on the average age of all your other customers?
That seems problematic.
It can be. You might smooth out the data too much and hide important patterns. But if you just delete every row that has a missing value, you might end up with no data left. It's a trade-off that engineers have to make every single day. You have to decide. Is it better to have less data that is 100% real or more data that is partially guessed? There's no single right answer.
And finally, in this section, we have the human loop, labeling.
Right. For most of the powerful AI we use today, specifically supervised learning, the AI needs a teacher. It needs labeled examples. It needs a human to have already gone through and said, this email is spam, this email is not spam, this is a picture of a cat, this is a picture of a dog.
It can't learn in a vacuum.
It can't. It needs that ground truth. And the source mentions a few ways to get it. You can have your internal experts do it, which is slow and expensive, but very accurate. Or you can crowdsource it.
Like with Amazon Mechanical Turk, where you pay thousands of people a few cents to label an image.
Yes, you have these massive armies of humans all over the world clicking on images of traffic lights to prove they're not a robot. But increasingly, the state of the art is AI-assisted labeling.
So you use an AI to help you label data for another AI.
Exactly. You use a dumb first-pass model to guess the label. Maybe it's 70% sure this is a cat. Then a human just has to verify it with a single click. Yes or no? It's much faster than labeling from scratch. But you still need that human eye for the final truth. You cannot fully automate the creation of truth.
Okay, so we have defined the problem. We have cleaned, processed, and labeled our fuel. Now we need the engine. This is section 3, model selection. And this seems to be the great debate in the AI world right now. Buy versus build.
It is the central strategic question for every CTO right now. Do you use a third-party API like OpenAI's GPT-4 or Google's Gemini, or do you build your own system using powerful open-source models like Llama or Mistral?
The API argument is pretty compelling, especially for getting started. Fast deployment, zero maintenance. You just plug into what is arguably the smartest brain on the planet.
It is incredible for things like general-purpose chatbots, summarizing text, or getting a prototype up and running in a single afternoon. The source compares it to renting a Ferrari. You don't need to be a mechanic, you just get in and drive. You don't worry about the engine, the tires, or the oil changes. You just pay the rental fee per mile and go incredibly fast.
But, like renting a Ferrari, it has its downsides. The source points out 3 big ones: privacy, control, and cost at scale.
Let's start with privacy because it's often a non-starter. If you're a bank, a hospital, or a law firm, you generally cannot send your customers' financial records or a patient's medical history to a third-party server owned by another tech giant.
Right. The moment the sensitive data leaves your building, it's a huge security and compliance risk.
It's often flat out illegal. Regulations like GDPR in Europe or HIPAA in the US for healthcare often require the data to stay on your premise, or at least within your own private encrypted cloud. In that case, you must build or host a model locally. You cannot use the public API. End of story.
Okay, so privacy is a hard line. What about cost? I would assume renting is cheaper than buying a whole supercomputer.
Initially, yes. For low usage, it's much cheaper. But API costs scale directly with usage. Every time you ask a question, every time you process a document, the meter is running. It's a cost per token per word. If your application starts processing millions of documents a day, that bill can get astronomical really fast.
It adds up.
It really does. Owning the model, that is, running a local open source model on your own servers, has a higher upfront cost. You have to buy or rent the GPUs, you need the talent to manage it, but the marginal cost per query is much, much lower in the long term. It's basically just the cost of electricity.
So it's the difference between taking an Uber everywhere versus buying a car. Uber is great for the occasional trip to the airport, but if your job is being a delivery driver and you're driving 500 miles a day,
You buy the car, exactly. If your core business depends on driving, you don't rent the car, you own the asset.
And then there's the concept of transfer learning. This feels like the perfect middle ground between the extremes of buying and building.
It is, and honestly, it's the most common approach for serious, specialized engineering work today.
The source uses the generalist doctor analogy, which I found really helpful.
Right. Think about how humans learn. You don't start from scratch every time you learn a new skill. When you go to medical school, you first spend years learning the basics, biology, chemistry, anatomy. You become a generalist doctor.
You know how the body works in general. You know the basics of disease.
Exactly. Large language models like GPT or Llama are generalist doctors. They've read the entire internet. They have a massive general understanding of English, logic, history, science, and facts. But they don't know your specific business. They don't know the specifics of your cardiology department. They don't know your company's unique billing codes.
So transfer learning is the specialization. It's like sending the general doctor to a cardiology fellowship.
That's the perfect analogy. You take that pre-trained model, that generalist, and you fine-tune it. You show it your specific proprietary data, your past medical records, your internal cardiology research journals. You teach it to be a cardiologist.
And technically, how does that work? The source mentions freezing layers.
That's the key to doing it efficiently. A neural network has many layers. You freeze the base layers, the parts that understand English grammar and basic logic, so you don't mess them up during this new training. You don't want the model to forget how to speak English while it's learning about hearts.
You lock in the foundational knowledge.
Right. And you only train the final, topmost layers on your proprietary stuff. This drastically reduces the amount of data and compute power needed. You get the billion-dollar benefit of the massive general training, plus the laser-focused specificity of your niche. It's the best of both worlds.
Moving on to section 4. We have our engine, whether we bought it, built it, or specialized it. Now, how do we drive it? The interface. The source describes prompt engineering as steering the model.
And it emphasizes very strongly that this is engineering, not just chatting. You aren't just asking nicely. You are programming the model with natural language. You are carefully crafting an input to manipulate the probability distribution of the next token it will generate.
It's a technical skill. One of the techniques mentioned is chain of thought prompting. This is forcing the model to show its work.
This is huge for reducing hallucinations and errors in reasoning. If you ask a model a complex math problem or a logic puzzle and just ask for the final answer, it might guess. It tries to jump straight to the conclusion and often gets it wrong.
Like a student who looks at the answer key in the back of the textbook, but doesn't know how to get there.
Exactly. But if your prompt includes a simple phrase like, let's think step by step, the model's behavior changes. It actually processes the logic sequentially. It generates the intermediate reasoning as part of its answer, and extensive research shows this significantly reduces errors.
Just by adding that one phrase, let's think step by step.
That one little phrase, it changes the way the model activates its neural pathways. It forces it to build a logical bridge to the answer instead of trying to teleport there. It's a simple hack with profound effects.
And another one is few-shot learning.
This is all about giving the model examples to follow. If I want the AI to classify customer support emails, I don't just say, classify this email. That's too ambiguous.
That's zero shot, no examples.
Right. Instead, I use a few-shot prompt. I say, here's an example of a billing complaint. Here's an example of a technical complaint. Here's an example of a positive compliment. Now, classify this new W email.
You're setting the pattern. You're showing it what good looks like.
You are orienting the model in the right direction. Those examples, the shots, ground the model in the specific format, tone, and categories you expect. It sees the pattern and follows it, leading to much more consistent and accurate results.
The source also gets very practical, mentioning JSON structuring. This feels very specific to the engineers in our audience.
It's absolutely crucial for any real-world integration. If you are building an application, you don't want the AI to write you a lovely paragraph about the data. You want code-readable output. You want a structured JSON object that can be parsed and plugged directly into a database or a front-end website.
So you have to explicitly tell the model in the prompt, output your answer only in JSON format. Do not include any explanatory text.
Precisely. Do not give me an intro. Do not give me an outro. Just the code. Because if the AI replies, sure, here's the JSON you requested, and then gives you the code, your software pipeline breaks because that first sentence, sure, here is X, is not valid JSON.
Right. You need machine-readable output, not a conversation. And finally, this brings the engineering discipline full circle, treating prompts like code, which means prompt versioning.
This is the sign of a mature AI engineering team. You don't just have a Google Doc where people randomly guess prompts. You track them in a version control system like Git. You A/B test them scientifically. Does prompt A cost fewer tokens? Is prompt B more accurate on our test cases?
You have a history.
You have a history. You use tools like PromptLayer or Langsmith to treat prompts with the same rigor as you treat your software code. You can see the performance over time. You can roll back to a previous version if a new prompt breaks something. It's about discipline, not guesswork.
Okay, let's zoom out a bit. We've been down in the weeds of prompts and models. Now let's look at the whole system. Section 5, the architecture. Because a model by itself is just a brain in a jar. It doesn't know anything about the world right now.
That is the core memory problem, or knowledge cutoff problem. AI models are frozen in time. If you ask GPT-4 about the stock price today, or about your specific company policy that changed yesterday, it doesn't know. It only knows what it was trained on, which might be data from a year or more ago.
It will confidently make something up based on old data.
Which is dangerous. And the solution that has taken over the industry is RAG. Retrieval Augmented Generation. I love this acronym because it's so descriptive. R is essentially giving the AI an open book test. Instead of forcing the AI to memorize everything about your company, which is impossible and expensive, you build a system where it looks up relevant documents first before it ever tries to answer.
Okay, so walk us through the flow. If I'm an employee and I use an internal chatbot to ask, what is our company's policy on vacation days? What happens behind the scenes with the RK system?
Great question. First, the system does not go to the large language model. That's the last step. The first step is your question, what is our vacation policy, is converted into a mathematical representation, a vector.
A vector.
Think of it like a numerical fingerprint for the meaning of your question. The system then goes to your company's knowledge base. All your HR documents, your employee handbook, which has also been pre-processed into these numerical vectors. It then does a search.
Not a keyword search, but a meaning search.
A semantic search. It looks for the document chunks whose meaning fingerprints are closest to your question's fingerprint. It will find the paragraph on page 12 of the employee handbook that talks about paid time off.
Okay, so it retrieves the relevant text.
Right. It grabs that text and only then does it go to the AI. It combines the retrieved text with your original question into a new, much more specific prompt. It says to the AI, using only this provided text from page 12 of the handbook, answer the user's question, what is our vacation policy?
So it completely prevents the AI from just making things up from its old training data.
It dramatically reduces hallucinations because the AI is grounded in the source text you just gave it. And crucially, it allows the AI to cite its sources. It can answer your question and then add, I found this information on page 12 of the employee handbook, section 4.1.
That seems infinitely more useful and trustworthy for a business. It turns the AI from a creative writer who makes things up into a reliable librarian who finds the facts.
It is the standard architecture for enterprise AI right now. If you're building a serious business tool that needs to use up-to-date factual information, you are almost certainly using RAG.
But the source goes further, talking about orchestration. It mentions tools like LangChain. How is that different from RAG?
LangChain is the glue that connects the dots. Our RAG is one pattern, but what if you need a multi-step process? LangChain and similar tools allow you to chain these steps together. You can build a workflow that says, Step 1, use the Google search tool to find today's news on topic X. Step 2, feed that news to the AI to summarize it. Step 3, take the summary and use it to draft an email. Step 4, wait for human approval, then send the email.
It's like building a pipeline out of AI components.
Exactly. It turns the AI model from a single-purpose tool into a component in a larger, more complex automated workflow.
But the cutting edge, and this is where I really leaned in while reading, is agents. The source mentions Crew AI. This sounded like science fiction again. multi-agent systems.
This is the big paradigm shift that's happening right now. We are moving from chatbots to agents.
Okay, so what is the fundamental difference?
A chatbot talks, an agent does. An agent has tools. It can browse the web, it can write and execute code, it can access APIs. And with multi-agent systems, you have specialization of labor. Instead of one monolithic AI trying to do everything, you create a virtual crew of specialist agents.
So you'd have, what, a researcher agent?
Exactly, a researcher agent whose only job is to browse the web, read documents, and find relevant data. It's really good at that one thing. Then you have a writer agent who takes the raw data from the researcher and drafts a coherent report. And maybe you have a manager agent whose job is to review the writer's draft, critique it, and send it back for revisions.
So they actually talk to each other. They collaborate.
In a sense, yes. They pass outputs back and forth to iteratively refine the result. The manager agent might say to the writer agent, "This analysis is too superficial. Go back to the researcher and ask for data on our competitor's market share." The whole crew then works on the new task.
That is wild. It's like managing a virtual team of incredibly fast, tireless interns.
It is, and it's much more robust than a single model because if one part fails or produces a weak result, the others can correct it or ask for a do-over. It's moving from systems that just generate text to systems that can autonomously execute complex, multi-step tasks.
But all this computing power, having agents talk to agents, querying vector databases, running these massive models, that has to be expensive. Which brings us to Section 6, the hardware and cost.
AI is expensive, make no mistake about it. And the source breaks down the cost into two main buckets: the cost of training and the cost of inference.
Training is the tuition you pay for the model to go to school. Inference is the salary you pay it to do its job every day.
That's a great way to put it. Training is the massive upfront cost, teaching the model from scratch. This takes supercomputers with thousands of GPUs running for weeks or months. It can cost tens of millions of dollars for a foundational model. That's why only a few big companies can do it.
But most of us aren't doing that. We're doing fine-tuning or just using the model.
Right. So for most people, the main cost is inference. That's the ongoing operational cost. Every time a user asks your ag system a question, the meter runs.
And the hardware that's running the meter is overwhelmingly GPUs. NVIDIA is obviously the big name here, the one that's dominated the market.
They are the workhorse of deep learning. Their CUDA software platform gave them a huge head start. But the source also mentions TPU's Google's tensor processing units.
What's the fundamental difference between a GPU and a TPU?
GPUs were originally designed for graphics for rendering pixels in video games. They have thousands of small cores, which just happens to make them really good at the parallel matrix math that AI uses. TPUs, on the other hand, are chips designed from the ground up specifically for the math AI does, called tensor math.
So they're more specialized?
They're ASICs application-specific integrated circuits. For massive scale AI workloads, they can be more powerful and more energy efficient, but they are proprietary to the Google Cloud ecosystem. You can't just go out and buy a TPU for your home server.
And the old debate between cloud versus on-premise infrastructure returns here with a vengeance.
It does. The cloud is incredibly easy to start. You can go to AWS SageMaker or Google Vertex AI, swipe a credit card, and have access to a powerful AI server in minutes. You pay for what you use. But the danger is, if you leave it running or your usage spikes, the bills can become astronomical. It's like leaving the lights on in an empty football stadium.
So what's the alternative for a company that wants to control costs?
The hybrid approach is gaining a lot of traction, which the source touches on. You do your heavy-duty training or fine-tuning in the cloud where you have access to practically infinite power for a short time. But then you deploy the finished model on the edge.
The edge, meaning not in a giant data center, but on local devices.
Exactly. Running the model directly on the user's phone or on a small server inside a factory or in a retail store.
But can a phone really run these powerful AI models?
The massive ones, no. But there's a whole field of research around model quantization and optimization to create smaller, highly efficient models that can. And if you can run the model on the user's phone, guess who pays for the electricity and the hardware?
The user does.
Exactly. And guess what happens to your cloud inference bill? It drops to zero for that user. Plus, it's faster because there's no network latency, it works without an internet connection, and it's better for privacy because the data never leaves the device.
That's the holy grail of deployment. Fast, cheap, and private.
It is. It's the future for many, many applications.
Which brings us to our final and maybe most important section, the safety net. Section 7, Ethics, compliance, and user experience.
Yeah.
Because if this stuff goes wrong, it can go wrong in very big, very human ways.
This all centers around the black box problem. Deep learning models, by their nature, are notoriously opaque. You put numbers in one end, magic happens in millions of interconnected neurons in the hidden layers, and an answer comes out the other end. It's very difficult to know exactly why it gave that answer.
And in many situations, that's not acceptable. If an AI system denies your loan application, you need to know why. You can't just have the bank say, sorry, the computer said no.
Legally, you cannot. In many jurisdictions like the European Union, you have a right to explanation under laws like GDPR.
So how do we crack open the black box? The source mentions techniques like Eshape and Lime.
These are explainability techniques. They essentially work by poking the model thousands of times to reverse engineer its decision. They can produce a report that says, the model denied this loan primarily because of these three factors, in this order of importance: a high debt-to-income ratio, a large number of recent credit checks, and a short length of employment.
So it turns the black box into more of a glass box. You can see the reasoning.
That's the goal. And that kind of transparency is absolutely essential for regulatory compliance. The source specifically calls out the EU AI Act, which is a landmark piece of legislation. It outright bans unacceptable risk AI, like government social scoring systems.
And it puts heavy restrictions on high-risk AI.
Exactly. Anything in hiring, lending, law enforcement, or medical diagnostics, it demands rigorous auditing, risk management, and human oversight for these systems.
And going back to bias, the source makes a crucial point. It is not enough to just delete the race column from your data set to prevent racism.
This is the proxy variable problem, and it's incredibly insidious.
Explain that.
Okay, so you're building a lending model. You're a good person. You don't want it to be racist. So you delete the race column from your data. You think you're safe. But you keep the zip code column in your data. And if your city is historically segregated, the AI can learn to use the zip code as a proxy for race.
So it learns that people from one zip code are a higher risk than people from another, which effectively recreates the racial bias you try to remove.
Exactly. The model learns that zip code 90210 is a good bet and zip code 90211 is a bad bet without ever seeing the word white or black. This is why you need active, continuous auditing. You have to test the model with hypothetical scenarios. If I take this approved application and change only the name to one that is stereotypically from a minority group, does the outcome change? If it does, your model is biased, even if you deleted the explicit labels.
And finally, this all ties into user experience, building trust with the person on the other end of the screen.
A huge part of that is the system admitting when it's uncertain. It is far better for an AI to say, based on the documents, I'm 60% sure the answer is X, but you should double check with HR, than it is for it to confidently lie to you.
The hallucination problem again. Confidence doesn't equal correctness.
Not at all. And for high-stakes decisions, medical, legal, financial, you must keep a humie in the loop. The AI is the assistant, not the replacement. It drafts the legal brief, but the lawyer reviews and signs off on it. It highlights a potential tumor on the X-ray, but the radiologist makes the final diagnosis.
You never, ever let the AI fly the plane solo on critical systems.
Not yet. And, maybe not ever for some things. The stakes are just too high.
So we have gone on quite a journey today. We started with the trap of solutionism, defining the problem before you touch any code. We talked about treating data like a living garden, not a dead oil field. We debated buying versus building the model engine.
We engineered prompts, we architected complex RD and agent systems, we looked at the hardware bill, and we put the ethical and safety guardrails in place.
It's a comprehensive journey. It really shows that the code, the actual Python script for the model, is just a tiny fraction of the overall work.
It's the very tip of the iceberg. The engineering, the architecture, the process, the ethics, that's everything underneath the water that makes the whole thing work.
I want to circle back to that agents concept for our final thought.
The
source suggests we're moving from chatbots that talk to agents that do.
This is the big shift. We are moving from systems that generate text to systems that can execute actions in the digital and eventually physical world. And as we build these, the single most important skill isn't just coding a model. It's architecture. It's understanding how all these different pieces, the data pipelines, the models, the safety checks, the cost controls, fit together to solve a real human problem without accidentally creating a dozen new ones.
There was a line in the conclusion of the source that really stuck with me. Treat your data like gold and your problem definitions like blueprints.
That sums it up perfectly. If you get the blueprint wrong, it doesn't matter how good your builders are, the building is going to fall down. If the data you build with is toxic, the building will be toxic too.
Stay ahead, become irreplaceable. That seems to be the goal here. It's not about being the best coder, but the best architect.
Absolutely. Think systems, not just models.
Thanks for diving in with us. We'll see you on the next one.